Okay, so one thing I'll touch on just before I talk about interferometry in space, it's worth coming back to a point that both Gerard and Gautam alluded to. At the wavelengths we're talking about, you have to mix the light beams together. At radio wavelengths, you can have amplifiers, you detect, you have a fully phase coherent signal, you beat it down to some intermediate frequency, you can amplify it. The VLA, ALMA make beautiful pictures with tens of arrays because they can completely fill all the spacings in the UV plane to really a remarkable level. Also, their diffraction limited beam takes in quite a lot of sky, so when you're populating that diffraction limited beam, you're getting quite a few arc minutes or many tens of arc seconds with lots of pixels. And Charlie Towns was right. It's the h nu over k value, which tells you what your quantum fluctuations are in, with your local oscillator or whatever. And if you're at 1 micron, h nu over k is about 10,000 degrees. That's your noise source. And if you're trying to look for something that's really faint, it's a killer. Plus, your bandwidth in an IF is a few 3, 8, 10 gigahertz out of the terahertz signal that you're trying to observe. And so when we talk about the advantages of interferometry in the radio, and then talk about what we can do in the optical or near infrared, the fact that the number of telescopes we can use, where we always have to combine the light beams with no amplifiers possible, is really a problem. It means we get very poor UV plane coverage. The angles we look at are small. So when we go to our astronomical friends and say, here's something we can measure, is it interesting? As opposed to the opposite version of Mazurka, which is law. This is interesting, can you help me study it? Those are sort of the problems that we have to deal with, and that's really independent of ground space or anything else. And it's our fundamental challenge to come up with interesting things for a broad community. We have a fascinating and important problem where infrared nulling, infrared interferometry is fabulous. It is interesting and we can measure it, but we just have to be aware that there's a real distinction between interferometry with ALMA is fabulous for everybody, not so much at these short wavelengths. So we really do have a challenge ground to our space. So I'm going to go quickly about the good, the bad, and the ugly about interferometry in space. The good, the wavefront quality and stability is fabulous. It's determined by the optics quality and maybe some local sources of vibration, 90% or greater Strel ratio at all wavelengths with JWST. And JW is turning out to be stable at lambda over 100 for a couple of days at a time. If you want to do closure phases for image reconstruction, again, very highly stable. That's really the equivalent of what you could do at radio wavelengths. If you want to move beams around from one place to the other, you don't need vacuum tubes. It's a vacuum. It's all good. And of course, if you want to do things in the mid-infrared, we've now demonstrated passive cooling to 45 Kelvin or less in the thermal infrared. I will point out, Sasha, you're going out to 18 microns. Give or take, JWST starts to see background from all of its different sources at somewhere between 12 and 15 microns. And that's at 40, 45 degrees. But what's happening there is it's not so much the telescope itself is contributing this background, it's sort of a diffuse glow of everything that's something like 10 to the minus 3 emissivity at 90 degrees, which just starts to come in, and there's just this glow of photons at longer wavelengths. So then there's the bad. Does that show up here? This is some more of the good. This is, you get to aim the interferometer, not the telescopes. We've shown earlier there's this whole question of the delay. If you have a 100-meter baseline, you have tens of meters of delay that you have to inject to make the path lengths equal, and we saw some very nice discussion of that from Gerard. Here's another view of the bowling alley that used to house the delay lines, and now, starting as of about 2 weeks ago, houses operational Keck Planet Finder, the new RV instrument for Keck, in a highly stable, basement environment, which is fabulous. But the delay lines and everything were there until a year ago, waiting for someone to come back and bring the interferometer back to life. For those of you who've seen Forbidden Planet, the Krell did not come back, and it never came back to life, which is really sad. The Keck interferometer, as you heard, was really a pathfinder in a lot of this. But aiming the interferometer and not the telescopes reduces the delay line problem, from tens of meters to less. And the first example on the ground, of course, is LBT, where you have two telescopes on a 14-meter separation, which I guess gives you, 23 meters of actual baseline. And you don't really need to correct anything for delay because both telescopes are always aimed right at your target. And of course, when we go up into space, that's the goal of something like LIFE or TPF. You've got a greatly reduced baseline delay line problem. So that's the good. What's the bad? Well, we're finding out with JWST, you can actually have impacts on the telescope that affect the telescope quality. Happily, for the NIRCam coronagraph, we mask out this entire segment because it has a strut going through it. So this particular zit did not affect the coronagraphic sensitivity, but this has become sufficiently a problem for LUVOIR and HABEX, IRU, whatever it's going to be called, that instead of having this nice telescope sitting above the sunshade just hanging out there in the breeze, they're now going to have a barrel to help protect the telescope. What else have we got? So if you're on separated spacecraft, you're not just having something like SIM where you have telescopes on a single strut. If you're more than something like 10 meters or so, each telescope in your central receiving station needs a full-up spacecraft. Precision 3-axis control, maneuvering fuel, power, communications, thermal control, sunshades, and the whole deal. Those are not cheap. You don't necessarily need the full communications capability to come back to Earth with your data. That could be in their central receiving station, but it needs a backup, so at least one other spacecraft has to have it, so maybe they all have to have it. It's a serious spacecraft. The beam transport, you don't need a vacuum tube, but you do need to protect this very tight beam that has your very low background signal that you're trying to measure in your interferometer. You have to protect that from any scattered or diffraction light or thermal radiation and any view of thrusters going off and so on. So if you look at the picture that Sasha showed of this out-of-plane central spacecraft getting the beams from all the telescopes, and you're aiming a telescope at that central receiving station back at these 2-meter telescopes with their spacecraft, a significant part of those spacecraft are at 300 degrees and emitting tons of 10-micron radiation. So you need a really tight beam that focuses on the beam combiner signal coming out of that spacecraft and no diffracted light from anything else or scattered light getting back into your beam at the central receiving station. So I actually think beam transport is one of the bigger challenges that we face. And then, just the problem is once you're at L2, things like repair, refueling, and all the things you'd like to do that you can do on the ground, you can't do in space. Then there's the ugly. Back at the 2010 decadal, I had this cartoon of the circular firing squad among the exoplanet community. I don't know if you can read all these things, but there's radio velocity and transits and astrometry and coronography and microlensing and all the different techniques people had, all saying we want to be the next decadal mission. And as a result of that decadal, we got basically nothing, and the dark energy people came in and said, well, we know what we want to do, let's go do it. Oh, by the way, we'll give you a little microlensing. I like microlensing. What?
Shouldn't you put names on each one of those guys?
I'm doing that to protect the guilty. Luckily in 2020, the community had actually focused in on direct imaging, and coronography is something that appealed to both the broad astronomy community as well as the exoplanet community. But these are long-term projects, they're expensive projects. In space, you need to get the disciplined people to agree not to shoot each other and come together. You need to bring the broad astronomical community along. You need to convince the funding agencies that you're doing something interesting. Here's a huge advantage that we have. Congressmen understand looking for life. They do not understand dark energy. Their kids understand, I want to find bugs on another planet. They do not understand dark matter. Appealing to the funding agencies is actually, I think, among the easier things we can do until they see the price tag. That's a problem. But in terms of the basic science, we have an enormous step up. And of course, we reach, as someone said earlier, to a very broad set of scientists outside of astronomy. The origins of life people, biologists, everyone understands that. So that, I think, an advantage, and also with the public. The other problem with space missions in particular, and it turns out now even very large ground-based systems, is it's a 25-year plus cycle to go through, early pre-formulation and design reviews and actually get to here. There's a step where you get to here, and then you go back to zero, and then you go to here, and then you come back again. But, then once you get up into this hump, there's sort of a natural project cycle. But being down in here can take a long time, and you really need a dedicated, multi-generational set of participants with clear paths for achievement, accomplishment, and advancement, and succession. So Malcolm and I are here to tell you, this project's now for you guys. But the nice thing is, as I said earlier, there's lots of great science along the way, and we need to be taking full advantage of that so that we have things for graduate students and postdocs to do, both from an instrumental standpoint and from a science standpoint. So this very quickly, there have been interferometers in space. Before, HST had the fine guidance sensor, which just helped track JWST. It used not two separate beams, but used the shear between two wavefronts to help track the system. And these are sort of what you'd get as you scanned in arc seconds, and you could actually get centroids on stars at the level of a milliarc second. And that was used to meet the pointing budget of HST that was about 7 milliarc seconds. You can go through this at your leisure. There's some articles here that talk about the FGS. But it actually produced some science early in the day, in sort of the pre-Hipparcos, pre-Gaia era. Measuring Cepheids in the distance scale was a key thing to do. Astrometry is hard, ground or space, but you compare the Gaia results to the HST results, they did pretty well. Some stellar diameters got measured, and some masses and orbits of known exoplanets. The major contribution of astrometry up until very recently has been to debunk radio velocity planets by showing that they were face-on planets, not edge-on systems, so that M sin I, actually the M was a brown dwarf and not a planet. There was SIM that's been talked about. I won't go into a lot of detail, but the goal was to measure lots of planets in the range of super Earths, and then even down to Earths themselves. 6 habitable zone Earths around at least 6 stars. 3 stellar interferometers, 2 to lock up and guide the whole spacecraft and the interferometer, 1 to do the science, to move back and forth between a target star and some reference stars. And there was even some imaging capability with multiple telescopes originally along the strut, so you could fill out the UV plane. And it was going to work pretty well. So it was originally recommended in the 1990 Decatur Report, quasi-endorsed in the 2000 Decatur Report, and after about $500 million of technology, it was killed in the 2010 Decatur Report in a footnote that said SIM is not included in the recommended program following the committee's consideration of other activities and the constrained budget. So, you go up, you go down, you get close, you go back, and it is just the way of the world, and you have to be convinced that the technique you're pursuing is the right one. I've boosted SIM for a long time. I was on the project. It died. I'm a big booster of radio velocity observations because we can do them. I'm skeptical that RV will actually get down to the 10 centimeter per second range that we need, not because of technical reasons. There are plenty of instruments soon to be available capable of measuring that. God did not give us stars that were quiescent. So we're stuck, I think, eventually going back to an interferometric astrometric mission. We'll see. And I'll just mention my last slide. There is interferometry with JWST. There's a non-redundant masking aperture where this is the interferometer on JWST. It's a few centimeters across. These holes give you separated telescopes, all held together very nicely by the JWST backplane and telescope. This is what the UV plane looks like from these particular configurations. Each one of these 7 holes gives you different non-redundant baselines. There's 21 of them. This is what the UV plane looks like. There's also an approach that's been developed more recently called kernel phase interferometry that tries to use the whole telescope. The advantages are you get lots of baselines, you get to work at lambda over 2D rather than 4 lambda over D for a typical LEO coronagraph. You have an outer working angle that's determined by lambda over the diameter of 1 meter diameter or so of the hole. You don't use the full area, and you do suffer the photon noise from unattenuated starlight, so that limits your sensitivity compared to a coronagraph that actually blocks out the starlight. So from a performance standpoint, those fun. Oh, that's too bad. Those didn't. I had 2 images here that did not get carried over into the Google Doc. In any event, you get a contrast of something like 7 to 8 magnitudes is possible with this aperture masking interferometer, but you're doing that at under something like 70 milliarc seconds, so those are millis, compared to the LEO coronagraphs or the 4-quadrant phase mask. These are all milliarc seconds. Outer working angle is confined here, but not for the other coronagraphs, and you don't get as much contrast, but you are getting it in very close. And that's it.